All right, so now what we're going to do is we're going to look at calculating molar masses or formula masses of compounds, and then also trying to calculate the percent composition of a compound. All right, so let's start by just with looking at an example. So consider ethylene glycol, so C2H6O2. And then for this class, anytime that we report a molecular weight, we want to report it to the nearest hundredth. Okay, so we should have 2 decimal places. Okay, so let's go ahead and for ethylene glycol, I've listed the atomic masses of all the atoms. So if we're looking at the mass of a single molecule of ethylene glycol, we'll just go through and take the sum of each individual component. So we have 2 carbon atoms. So we'll have 2 times 12.01 AMU. We have 6 hydrogen atoms. So it'll be plus 6 times 1.01 AMU. And we have 2 oxygen atoms. So that'll be plus 2 times 16.00 AMU. Whenever we add all those up together, we should get a molar mass of 62.08 AMU. And just remember, if you see AMU, this is talking about a molecule, the mass of a single molecule. But you can also write that same value, 62.08 grams per mole. And this is looking at 6.022 times 10 to the 23rd molecules. Let's try that again. Okay, so the grams per mole is looking at if you have 6.022 times 10 to the 23rd molecules. So if you see AMU, it's the mass of a single molecule or atom or formula unit, but grams per mole is talking about there being 6.022 times 10 to the 23rd of those entities. So one of the next things we're going to talk about is the difference between a formula and a molar mass. So is there a difference between formula mass and molecular mass? Well, technically yes, but sometimes we don't really differentiate. Many times we'll just ask for the molar mass even if it's a formula unit. So a molar mass is the sum of the atomic masses of all of the atoms in a molecule. So this is looking at a covalent molecule. So there's a lot of nonmetals bonded together. So for instance, we just looked at ethylene glycol, C2H6O2. So we would find the molar mass of that. But then a formula mass would be the sum of the atomic masses of all atoms in a formula unit of any compound, molecular or ionic. So this would imply if we're looking at, for instance, sodium chloride, and we know that that is a binary inorganic compound. So there's sodium ions and chloride ions. But many times we will interchange these terms, but you should be aware that they do have different meanings. So let's look at calcium nitrate. Okay, so here we want to determine the formula mass. So here's our cation calcium. So calcium would have a 2+ charge. And then nitrate, NO3, would have a -1 charge. So be careful whenever you have something with parentheses and then a subscript here, because we're going to need to distribute that throughout. So let's go ahead and start by figuring out, well, how many calcium atoms do we have? Well, we have 1 calcium atom, so we'll have 40.08 AMU plus, how many nitrogen atoms do we have? Well, there's 1 per nitrate subunit, but then this 2 up here, that tells us that there are 2 of the nitrate, so we'll take 2 times 14.01 AMU plus how many oxygens do we have? Well, there's 3 oxygens per nitrate, but then there's 2 of them, so that's a total of 6. So 6 times 16.00 AMU. And then once you add all that up together, you should end up with something around 164.10 AMU. So whether you're looking for a molecular mass or a formula mass, it's still the same process for either of those. Let's go ahead and look at percent composition before we quit for the day. So percent composition, this is just like any other percent that you would find. So for instance, if you were going to be looking at the percent of I, or maybe you're looking at your percent that you got correct in a class, well, let's look at it in terms of mass. We'd take the mass of I divided by the total mass, and then we'll have to multiply that fraction by 100%. So we're looking at the relative mass of an element compared to the entire compound. Let's go ahead and look at sodium chloride, for example. So sodium has a mass of 22.99 AMU. Chloride has a mass of 35.45 AMU, and then the compound has a total mass of 58.44 AMU. So if we're looking at the mass of sodium, what we'd have to do is we'd have to take the mass of sodium for the percent composition over the total mass, which we'll write as m tot, times 100%. Okay, so now we can just plug in our values so we can calculate the percent composition of sodium. So we would have 22.99 AMU divided by 58.44 AMU times 100% equals 39.34%. So in the compound sodium chloride, 39.34% of that mass comes from the sodium ion. So then we'll repeat the same process for chlorine. We'll take our mass of our chlorine, which is 35.45 AMU, divided by the total mass, which is 58.44 AMU. Multiply that by 100%, and we'll end up with a percent composition of chlorine in this compound to be 60.66%. Okay, so usually if you're finding a percent composition, we tend to, in terms of sig figs, go to a common decimal place. And so if the majority of things are measured to 2 decimal places, then we might go to 2 decimal places. Just, you're going to have to use your intuition as you're starting to calculate these. Another way that you could calculate the percent mass of chlorine is, since there's only 2 components here, what you could have done is you could have taken 100% minus 39.34% and gotten the same answer. Okay, you can only do this if there's 2 components in our system, or whenever you're calculating the percent composition of the last component. All right, let's do one more example. So let's go ahead and calculate the percent composition of carbon, hydrogen, and oxygen in ethanol. So in this particular instance, I've given you the masses of each of the atoms, and we need to go through, before we do anything, we need to find the molecular weight. Okay, so in this particular formula, there are 2 carbon atoms, so we'll have 2 times 12.01 AMU. Okay, now how many hydrogens are there? Be careful here, because the way that this formula is written, it's written more as a structural formula, so we know how things are bonded. But we have 5 hydrogens here, and then 1 hydrogen over here, so for a total of 6. That's 6 times 1.01 AMU, plus we have 1 oxygen. So if you add all those together, you should end up with a total molecular weight of 46.08 AMU. All right, so recall, for finding the percent composition of carbon, we'd be looking at the mass of carbon divided by m tot, so the total mass, times 100%. All right, so let's go ahead and plug in for carbon. There's a total of 24.02 AMUs from carbon, divided by 46.08. Multiply that by 100%, and you should get 52.13%. Now for hydrogen, we'll take the 6.06 divided by the total, which is 46.08, times 100%. And this should end up equaling, if we're doing sig figs, it would be 13.2%. But since the carbon and the oxygen are both going to be reported to 2 decimal places, I would probably go ahead and report it like this, but I'm not going to count off if you reported this as 13.2%. Okay, so you can make a case for either way. And then for oxygen, you can either subtract both of these percent compositions of carbon and hydrogen for 100, or you can just plug in 16 divided by 46.08, multiply by your 100%, and that should give you 34.72%. Okay, so hopefully you have a good idea on how to calculate molar mass or formula mass for a given compound, and then also go through and find the percent composition.